Hello everyone, we're the Arterial Stent team. Arterial stents have been used to treat vascular disease all over the body which restrict proper perfusion of blood. The constriction of these vessel walls are due to the plaque buildup over time and caused by genetic predispositions and poor lifestyle choices. In this project, we aim to model different stents under different conditions. Here we have 3 different CAD models that we developed with other model additions in our tests for testing different anatomical conditions. For the material, we apply medical grade nitinol. This is unavailable as a default in SOLIDWORKS, but we did research about the material properties and inputted it as a custom material.
Thank you, Kevin. The objective for a nonlinear static study is to identify the force we applying to the inner surface of a stent and the pressure which is necessary for the balloon to expand the stent. In the stent-only model, we're adding the 10 Newton load to inner surface stent, and from the result of both response curve and animation, we can see the expanding is not uneven, and the load is force which is uncommon in the real life, so we have to add a balloon to the part. And the balloon is made of PET, it's a plastic material, and the load is 3 kilo atmosphere to inner surface of the balloon. The fixture is green arrows in the figures. From both animation and the response curve shows the expanding is more evenly, non-linearly is more close to the reality, which is better for the future analyze. I move on to Kevin for the steady state thermal analysis.
Thank you, So Young. For our next analyses, I performed steady-state thermal analysis to explore how the different stent designs respond to internal body temperatures when deployed, and the effect of thermal stress on the structure of the part. Internal body temperatures is roughly 98 degrees or 308 Kelvin. This temperature was applied to all exposed faces of the stent, which accounts for the blood flow to pervade the stent. For the boundary condition, since it was a thermal analysis, I checked the soft springs to use to stabilize the model. For the mesh, I utilized 3 different element sizes with decreasing size for each test iteration. Here are the results of the 3 different designs for the thermal analyses and 3 different test iterations. As you can see, the temperature results and thermal stress displacement results remain consistent and similar as we progress through finer mesh element sizes. For some visual representation, this is how the thermal stresses were distributed throughout the different designs, and the results of the analyses indicate that the designs and material in the design should not experience any problems when implanted into our bodies.
The purpose of our frequency test is to identify where each model is likely to break and how each model is likely to deform. What we are looking for in our designs are protrusions that could potentially be hazardous to the veins, and if each design will bend or concave. Here is a table showing the pros and cons of each model. We scored them from best to worst, with Model 1 being the worst, Model 2 being intermediate, and Model 3 being the best.
I ran the fatigue studies. Using the static studies, we ran fatigue analyses to determine the percent damage done to the stent structure over a period of time. We ran the study for 42 million cycles due to the fact that the average human heart beats approximately 42 million times a year. Here's a table for the data run in the 3 models when our first set of boundary conditions are applied. Here are the same 3 models, but with the second set of boundary conditions applied. After running the fatigue analyses, we discovered that Model 1 fails within the 42 million cycles, meaning that it would not last a single year within an artery. However, due to the fact that Models 2 and 3 are below the minimum SN curve, they are not expected to fail within a year. Ranking our designs, Model 1 would be the worst, then Model 2, and Model 3 would be the best. Model 3 is considered the best of the designs, and its only downside is it being less malleable than Model 2. However, it is still enough to be implanted safely.
Thank you, Jeremy. We rated all the designs on a scale of 3 between each other per each testing criteria, and design 3 from the test came out to be the better design of all of them. Our final design choice comes down to these 3 points that we've taken heavily into consideration as we designed our stent and performed our analysis. Here are our references, and thank you for your time and attention.